Welcome back, everyone. If you're focused, ready to learn, and looking for that absolute direct path to understanding, well, you're in exactly the right place. Today, we're diving into something I like to call the alchemist's approach to the Cambridge Additional Mathematics exams. We're going to strategically deconstruct Review Exercise 3 from the official syllabus. We aren't just going to look at the answers here. No, we're going to look at the actual anatomy of the questions. We're transforming raw baseline mathematical knowledge into absolute gold standard exam execution. But before we continue with this explainer, make sure you subscribe to our YouTube channel Ace the Exams at acexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's talk numbers, specifically the number 51. The questions we're analyzing from this specific review exercise are worth a grand total of 51 marks. Think about that for a second. That is a massive chunk of your final grade. Mastering the specific problem-solving patterns we're about to look at isn't just, good practice. It is pure gold for your results. When you learn how to decode what the examiner actually wants from you, those 51 marks stop being intimidating and they start becoming entirely predictable. Okay, let's dive into this. We have 4 distinct mathematical missions on our agenda today: coordinate geometry in circles, transforming nonlinear equations, mastering circular measure, and finally, trigonometric graphs and identities. First up, Section 1, Coordinate Geometry and Circles. Let's navigate some shapes. All right, here is question 1 from our source material. You're given a set of coordinates, and then you're hit with this command. Find the equation of the perpendicular bisector of CD. Now, I want you to mentally map out how you'd approach this. You have points C and D. What is the actual relationship between them that the examiner is testing? They don't just want a random equation. They want to see if you understand the underlying geometric properties that actually lock that line into place. And this brilliantly illustrates how we can break down abstract algebra into a really concrete roadmap. To get top marks here, you just follow 3 non-negotiable steps. First, if needed based on the given lines, find your points of intersection. Second, calculate the exact midpoint of line segment CD. Why? Because a bisector absolutely must cut right through the middle. Third, determine the perpendicular gradient. If you know the gradient of CD, you just flip it and reverse the sign to get your perpendicular slope. Once you have that midpoint and that new gradient, constructing the final equation is a total breeze. Let's move on to question 5 and see how this builds. Here, you're asked to show that the point 2, 8 lies inside a specific circle, and then deduce that a second circle touches it at only one point. The crucial part here is the strategy. You don't need to graphically draw this perfectly to prove it. To show a point is inside a circle, you simply calculate the distance from the circle's center, which in this case is -1, 4, to your point, 2, 8. If that distance is strictly less than the circle's radius, which is the square root of 100, so 10, then boom, it's inside. Easy, right? Then for the second part, deducing they touch at one point just means proving the distance between their 2 centers is exactly equal to the sum or the difference of their radii. It's pure, elegant logic. Moving right along to Section 2, Transforming Nonlinear Equations. Let's talk about straightening curves. This brings us to the core challenge of question 2. You're given an experimental relationship, y equals a times x to the power of n. Now, obviously, that's a curve, but the examiners want you to calculate the constants a and m using a straight line of best fit. So how do we mathematically flatten an exponential curve? Well, we need to reach into our toolkit and pull out logarithms. Just think about this transformation for a second. We start with our nonlinear curve, then we apply the natural logarithm, ln, to both sides of the equation. Through the absolute magic of log rules, ln y equals n times ln x plus ln a, why does this actually matter? Because it perfectly mirrors the standard equation of a straight line, y equals mx plus c. Our y-axis is now ln y, and our x-axis is ln x. That means our original exponent, n, is simply the gradient of this new line, and ln a is our y-intercept. It's a real game changer. So the examiner gives you data points for this line of best fit. Specifically, an ln x value of 1.35 pairs with an ln y of 4.81. Another point is 5.55 on the x-axis, pairing with 2.29 on the y-axis. By plugging these specific coordinates into our standard gradient formula, change in y over change in x, you instantly find n. Once you have n, just substitute one of the points back into the equation to find ln a, and simply take the exponential to find a. You've mathematically straightened a curve to reveal its hidden secrets. And hey, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to aceexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, on to Section 3, Mastering Circular Measure. Time to deal with fixed boundaries. Now, before we solve anything in this section, we absolutely must lock in this critical definition: the radian. It's a unit of angle measure based entirely on arc length. What you absolutely need to take away from this is that the advanced formulas for sector area and arc length that you're expected to use in these exams, they only work if your angle is in radians. If you try to use degrees, your calculations will instantly fall apart. No way around it. Let's look at question 6. I always recommend listing out the parameters before you start any heavy lifting. We have a radius of 8 centimeters. Angle AOB is an unknown, theta radians. Angle COD is 1.4 radians. And crucially, the area of sector AOB is given as 20 square centimeters. By organizing the raw data like this, you can clearly see all the puzzle pieces before you even try to assemble them. From there, the execution is incredibly simple. Step 1. Write down your area formula for a sector, which is 0.5 times the radius squared times theta. Set that equal to 20. Since you already know the radius is 8, the only missing variable is theta. Solve it. Step 2. Now that you have theta, the next part of the question asks for the arc length. And the formula for arc length in radians is beautifully simple: radius times theta. Just substitute your newly found angle, and you've secured full marks for this section. Finally, we reach Section 4, Trigonometric Graphs and Identities. Time to deconstruct trig. Question 7 gives us the curve y equals a plus b times sine of cx. We are given specific descriptive parameters, and we need to map them to the constants. Creating a mental map or a quick structured table decodes this perfectly. The amplitude is 4. Well, amplitude is governed by the multiplier in front of the sine function, so b is 4. The period is pi over 3. Now, the standard period of sine is 2 pi, so 2 pi divided by c equals pi over 3, which means c is 6. Finally, plug in the given coordinate point, pi over 12 and 2, into your newly updated equation to isolate and solve for a. Honestly, don't let the trigonometry scare you. It's really just parameter mapping. Now, check out question 8. Show that this massive fraction equals tan a. When you see a show that command in your exam, I actually want you to smile. It is literally a gift from the examiners. They are giving you the exact destination. You know precisely what the finish line looks like. You just need to document the journey to get there. And here is exactly how you document that journey. Think about the numerator, 1 minus cos A times 1 plus cos A. That is a classic difference of squares. When you expand it, it becomes 1 minus cosine squared A. Now recall your fundamental Pythagorean identity. Sine squared plus cosine squared equals 1. Therefore, 1 minus cosine squared A is simply sine squared A. Now look what happens. Your numerator is sine squared A, and your denominator is sine A times cosine A. One of the signs cancels out from the top and bottom, leaving you with sine A over cosine A. And what is that? It's exactly tan A. The complex fraction elegantly collapses perfectly into place. But wait, the question doesn't stop there. Part B hits you with, hence solve that exact same massive expression, but this time with 2x instead of a, set equal to 1. The key word here is hence. In Cambridge exams, hence is a strict command. It demands that you immediately recycle the identity you just proved. Whatever you do, do not try to resolve the massive fraction. You just proved that the whole left side is equal to tan. So because the angle is 2x, the equation simply becomes tan 2x equals 1. Suddenly, solving for x between 0 and 180 degrees goes from a complete nightmare to a basic trig calculation. So, the core strategy here, the real alchemy of mastering this paper, is decoding the examiner's command words. When you see show that, the destination is already known. Your focus shifts purely to showing clear algebraic steps. When you see hence, you know the previous answer is the absolute key to unlocking the current one. Decoding these commands transforms exam panic into a crystal clear execution plan. And listen, students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainers. Here is your final reminder. Subscribe to our YouTube channel, Ace the Exams, at aceexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at aceexams_IGCSE and click that bell. Don't let another exam pass you by. And that brings us to the end of our explainer. We've conquered coordinate geometry, flattened nonlinear curves, mastered radians, and collapsed those intimidating trig identities. The knowledge is mapped out, but the execution is entirely up to you. So I'll leave you with this question. Which of these 4 mathematical missions will you tackle first in your very next practice session? Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the exams. Your Cambridge success starts here. Take active ownership of your learning, apply this deconstruction strategy, and turn your next exam into gold. Thanks for joining me today, and keep focused.